Okay, so in today's class, we are going to review the basics of the linear algebra and the probability and statistics, of course, that you need to know, the concepts that you need to know in order to be able to study the machine learning algorithms. So the first thing that we are going to do is start with linear algebra. And let's say, this is linear algebra. Oops, it's too big. Let me just, that's better. So in linear algebra, let's start with the basic concepts, which are some of the basic concepts like scalar values, right? First one is the scalar value. Let's say, what's a scalar value? You guys can see my screen? No, right? So
Hocam açık değil.
forgot to share my screen. Okay. Now you can see, right? So scalar value is what is just a single number. It is just a single number that represents magnitude. Magnitude, right? Okay, so next we have what? The vectors, right? Next we have vectors. And the vectors is the set of numbers. It's the set of numbers. And for example, in real life or physical life, we are using vectors, for example, to represents the direction and the magnitude of a car, for example, right? That's why we need vectors. Okay, in general, we are gonna write, okay, the single numbers, for example, if x is a single number, I'm gonna write it as just like something like, okay, so just write in normal font X, okay? If I want to write the vector of X, if X is a vector, then I'm gonna write it in bold, right? So such as this one. So vectors will be bold, okay? When we are doing the notation, we're going to use the bold font for the vectors X. Okay, and next, what we have matrices, right? For that, okay, let's also find the matrices. Then we are going to go to the first. Right, something like this. X is equal to what? Generally, what we are going to use the square brackets to represent the elements of the vector, okay, such as that will consist of what? Set of scalar numbers, x3, xk, etc. Okay. That's a vector with k elements. What we said, the matrices. The matrices are two-dimensional arrays, and those two-dimensional arrays means that we are combining the vectors, column vectors or row vectors, right? Either column-wise or the row-wise. If you combine the vectors, we are going to get a matrix. All right. So matrix, we can say it's a two-dimensional array. Two-dimensional arrays. are called two vectors. Okay, and generally we are going to use the vector with capital letter. Okay, so for example, let's say this is x. X is the capital X, and it's a bold letter. It will be a bold letter, and then this is equal to. Let's use some scalar numbers here. x11, x12, x13. For example, let's say we have a 3 by 3 matrix. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay. And it's a 3 by 3 matrix. Okay, so we have 3 columns. Also, we have 3 rows. Okay, 3 rows and 3 columns. Now let's look at some properties of the vectors first, and we can use the vectors as column vectors or row vectors. Okay, some can use them, or let's say, let me just write it here, vectors. Let's go back to the vectors. And if I write it in this way, for example, let's say x is equal to, this is bold, right? So this is x like this. Okay. x1, x2, blah, blah, xk. If vector is shaped like this, meaning that this is k, actually this is what we can also say, that this is a k by 1 matrix, right? Because we have only 1 column but k rows. So we can also, I mean, every vector can also represent it by matrix, because there's either 1 row or 1 column. So there's just 1 column here. So we can say that this is a column vector. The other part, and we can say, if we take the transpose of this one, right, so like this transpose, then this will be what? x1, x2, blah, blah, xk. And this is what? Now 1 by k matrix, and this is called the row vector. This is column vector, and this is a row vector. Then, we can look at this. Let's say I have 2 vectors. Okay, multiplication of the vector. Which we are going to use a lot when you go to the machine learning algorithms. Most of the stuff we are going to do is multiplication of the vectors or matrices. Okay, so it's important that we learn this stuff. And if we have 2 vectors, let's say u, let me make it this one. Is there a shortcut for this one? No, I guess. U is equal to u1, u2, un. And we also, let's say we have another vector v1, v2, vn. Right? So this is v. We have 2 vectors with u and v. Right? So the concept is not here. Okay. This, I think it would be better if I use PowerPoint, maybe. I'm going to take this master PowerPoint also. However, I'm going to copy the other stuff also in the PowerPoint just for now. Let's go with here so we don't lose time. Okay, so we have vectors u and v, we said, right? And we are going to multiply it. And the multiplication of vectors, there can be two multiplications, which are that for example, inner product. Okay, this one. So inner product, or it is said dot product. Okay. The inner product, if we assume our vector is a column vector, let's say u. Okay, so well, you get the understand, right? I'm not going to always switch to the bold and the thin font, but you guys are going to understand this is a vector. Okay, so this is a vector. Let's say I have a column vector like this: u1, u2, un. Also, the column vector of v, v1, v2, blah, blah, vn. Dot product meaning that if I just use this sign, okay, just dot sign, it means that this is a dot product. U times v is just gives me the summation of the vector elements. Okay, so we are going to multiply u1 with v1 plus multiply u2 with v2, blah, 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 plus multiply un with vn. Okay, so this will be like this. So let me make this one a little bit bold so we understand these are vectors. Okay, then u1 v1 plus u2 v2 plus dot 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 un vn. Okay. Also, we can show this one as, I mean, this is just when we expand the whole equation, whole expression, we are going to get this. If we want to express this as a matrix multiplication, it will be what? U transpose times v, right? Or that is also equal to the v transpose times u. Okay, these are vectors, right? So let me make those a little bit bold. Okay. So because since, look at here, if I take the transpose of this one, it will be something like this. U transpose will be what? U1, U2, U3. Let's see, U2 just one word. About that. Un. Okay. If I multiply this with this one, what will happen is gonna what? It's gonna multiply this row with this column and sum all the elements, right? It will be the same as u1 times v1 plus u2 times v2, blah blah blah, plus un times vn. It is the same, right? Okay, so next let's go to the so let me show you this one is in Python. Let's open a Jupyter notebook. Let me just open a Jupyter notebook. Just give me a few seconds.
Hocam ekran hala değişmedi bizde.
Can I have a question?
Ekran değişmedi hocam, hala biz aynı ekrandayız da.
Just a second, it's still opening. Okay, now it works. All right, let me just change the name also so I can share with you guys. Review, let's say, review linear algebra and probability. All right, so for linear algebra or for all vector and matrix calculations in Python, we are going to use NumPy library. Okay, it's the NumPy library that allows us to all do vector and matrix calculations. Let's say just import library, import NumPy as MP. Okay, this is gonna import NumPy library. Then we can just create some vectors. Let me create some random vectors, let's say. And I can do this by using, let's say, u is equal to mp dot. In NumPy library, there's a random module. And in random module, we have rand int. Yep, this is here. Rand int function. Rand int function, it generates random numbers between specified numbers. Like we're going to specify the numbers. For example, I'm going to specify between 0 and 10. I'm just going to say that. And in a tuple, we're going to give the size of the vector. So we want this one. Let's say it's just a vector. If we want to use just a vector, we are going to give just one dimension. And I'm going to say I want to create a vector with 5 elements. So in tuple, we are doing this. So it means that we are entering a tuple. First element or the first dimension is 5 elements. So we are generating a vector of 5, okay, size 5. And we are not adding any other dimensions to this vector, okay? So this means that we are just creating a vector u with 5 elements. Let us print u so you can see better what it is. So you can see that we just created some random numbers between 0 and 10, okay, with the size of 5. Okay? I'm going to do the same for the v vector. Just copy and paste it. If you guys have Python, you can use this one. So we have v also here. Let's just print both of them so we can see our calculations. Print u and print v. Okay, so now let me open another cell here. All right. Okay, so if you want to do a dot product or any product of these two vectors, we can do it in 2 different ways. For example, if we just say u times v, what is it gonna do? In NumPy, all the vector and matrix multiplications or any arithmetic operators between 2 vectors or 2 matrices is element-wise, meaning that we are multiplying the first element of u with the first element of v. Also, we are multiplying the second element of u and second element of v. So the result will be the same size of these vectors, with just each element is multiplied with the other. Okay, so we have an array of, again, you can see 5. Let me just say print, it will print here. Okay, so here, yeah. So 9 times 4, 36, 4 times 7, 28, and so on. Okay? So we are doing all the multiplication or all the operations element-wise. So if you want to do dot product, what was that product? That product means that 9 times 4 plus 4 times 7 plus 7 times 1, and so on, right? So what I need to do is I just need to sum all these elements also. Then what I'm going to say, mp.sum. This is the function, numpy's function that sums all the elements in a vector. Okay, so here I'm going to create the vectors by multiplication of all the elements. Then I'm going to sum all those multiplications, which will give me y75. This is the first way. All right, so let me write. I want to say first way of that product. U times V. Okay. And the second way U times V is just, so as you guys remember what I said, it is the same as taking the transpose of any one vector and multiplying with the other. Okay, this is we can do in matrices. I mean, we can take the transpose of the matrices, but the thing is in NumPy or in NumPy in Python, okay, it does not recognize as a matrix. Okay, the vector is not recognized as a vector, so we cannot do it. All right. But what we can do is this one. There's another thing called MP dot. Let me say MP times dot function. Okay, we can use the dot function. Dot function is the dot product or the inner product. It's the same. If we say U and V, then it's gonna give me the same result like this. Okay, 81. So I can just say print this one. We can use this one, MP dot. All right. Or if we did this one, so this is the matrix multiplication. Actually, this is U times V. What does this one do? Just doing the matrix multiplication. Okay, so the matrix multiplication of U, V, if the elements are equal, then what does this one do? Actually, this one does exactly the same thing. If these two are vectors, this is equal to the U transpose times V. Okay, so if these two are vectors, not matrices, then what does it do? The NumPy dot function is just multiplies all the elements, then sum them up. So this is the vector multiplication. Okay, so let's go to the next concept of orthogonal vectors. Oops. Just use this part. Orthogonal vectors are defined as if the angle between two vectors are 90 degrees, then we say that these two are orthogonal vectors. Okay, so if I have, for example, let's say, oops. Better, what I can do is just one. Oops. Bring those lines. Sec. Give me a second to get familiar with this one. Okay. Now I'm gonna add another line like this. Nice. Okay, so if this is make this one 0, so it is horizontal. If I make this one 0, it will be vertical. Okay, so if I have exactly, let's say this is here 1 and 1, and another vector here -1 and 1. Okay, this is 1 and 1. Okay, and if you do this, you can see that the angle between these two vectors is 90 degrees. So we can say that if this is x and this is y, x and y are orthogonal. One of the important concepts of an orthogonal vector is what? The dot product x and y will be what? You guys remember? What's the dot product of two orthogonal vectors?
0.
0.
This is what, Karen?
0 hocam.
0, right? Okay. So you can say, check this one as 1 times 1 minus 1 minus 1, 1 times 1, 1. The summation is what? 0. So another thing that we are gonna see, or let's say, okay. So think as that I can say just a sec. Let me write coordinate system. Okay. All right, so or maybe I will come to this one later. So, okay, let me first go to the, let's go to the I'll come this to basis to later. We're going to deal this one with later. Okay. Okay. So let me define, for example, we are going to need this one also, the linear functions. So how we can use the linear functions. So we can use the vectors as inputs and outputs of a linear function. For example, let's say I have a linear expression, something like this. y1 is equal to a1 times x1 plus a2 times x2 plus an times xn. And y2 is also b1 times x1 plus b2 times x2 plus blah 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 bn times xn. Okay. So next I'm gonna show you. So for example, if you look at this one here, we can show this as a multiplication of two vectors, right? For example, y1 will be equal to the what? Let's say here. Let's say, let me make it a little bit bold. A is equal to A1, A2, blah, 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 AN, right? And X is equal to X1, X2, blah, 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 Xn. So we can write this Y1 as what? A transpose, or let's say inner product, A times X. So the linear functions can be written as inner product of two vectors, such as like that. So we're going to expand this one. We're going to add also y1, y2, and the other outputs, and then we are going to write the, or we will be able to write the whole linear functions, whole the set of linear functions by the multiplication of the matrices, which we are going to see right now. Okay, let's look at the matrices now. Okay, then matrices. As we said, the matrices are defined as the set of row vectors or set of column vectors. And we generally represent the matrix variable or the name with the capital letter. Okay, let's say M. I have a matrix of M, and M is equal to what? M11, M12, blah, 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 M1K. Or M21, M22, M2K. Go to here, MN1, MN2, blah, 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 M and K. Right? So this is M by K matrix. And so first, let's look at what we can do with matrices. The matrix we can take the transpose of a matrix, right? So the transpose of a matrix was what? I say transpose. What we are doing when we take the transpose, we take the rows, we use the rows as columns, and we use the columns as rows, right? So the M transpose will be what? M11, M12, M1N, right? Let me say, give another thing, not M. So it will not be the same as the here. Let me say what? K? No. I'm going to say A. Okay. And here A, 2, 1, A, 2, 2, A, 2, and again here A, K1, A, K2, A, K, and the M transpose becomes what? K times M. Like this. So for the M transpose, the value or the value in the ith row and the jth column is equal to the original matrix. In the original matrix, jth row, ith column. Okay, so we are just exchanging the subscripts over here. Okay. So let's look at the Jupyter notebook also, how we can create matrices. I'm gonna again use the same thing, let's say the same random numbers. Okay, so let me say this is M is equal to MP times MP dot random int, and here let's say I want to create 3 by 4 matrix. Okay, so here I'm writing the number of rows, then the number of columns. If you look at the print M, as you can see, we have a 3 by 4 matrix with just random numbers between 0 and 1, 10. Sorry. Okay, when I said, just a reminder, when I say between 0 and 10, 10 is not included, right? 0 is included, but 10 is not included. Okay, so this is the matrix. Let's look at the transpose of it. Right. So if you want to get the transpose of a matrix, what we do is MP dot transpose. Right. So from NumPy library, we are just using the transpose function of M. Right. So if I just take the transpose, you can see that we are just what? This is 3 by 4 matrix, and this is 4 by 3 matrix, becomes 4 by 3 matrix. All right. So another important concept in matrices is the identity matrix. Identity matrix is what? It's nothing but, let's say, identity matrix. Generally, represent this one with capital I. That is equal to once on the rows, diagonal. Okay. Once on the diagonal and 0 everywhere else. So identity matrices are always square matrices, means that if there's the same number of rows and the same number of columns, so if there's n number of rows, then there's n number of columns. So that's why we call this identity. And the diagonal is 1, then the other were, all the others are 0. Okay. So if we multiply some matrix, okay, let's say M is a sum matrix, I'm going to put it here. M times I, this is a matrix multiplication, right? You guys remember the matrix multiplication. The M times I is equal to the what? The matrix itself. Or I times M is equal to the what? The matrix itself. Okay. So the identity matrix is just like 1 in scalar numbers. Okay. And the inverse matrix, inverse of a matrix is the matrix that satisfies the following condition. Let's say if A, we have a matrix of A, we have matrix A inverse is the inverse of matrix A if and only if A times A inverse is equal to identity matrix, also A interchangeably A inverse times A is also identity matrix. So let's look at it. Let's look at the identity matrix first. Let's look at the identity inverse of the matrix. Okay. And let me go to the Jupyter notebook again. Let's say we have matrix A, and that is nothing but random numbers. I'm just going to take this one. Let's say matrix A here. Okay. Or first, before that, let's look at the identity matrix, right? I is equal to, we can create identity matrix by using the I function of NumPy, MPI. And here I'm just going to give one number because what we said, it was a square matrix. So if I just enter 5, it means that it's going to create 5 by 5 matrix with the diagonals equal to 1 and 0 others everywhere else. Print I, let's say, okay, print I. As you can see, we have 1s in the diagonal and 0 everywhere else. Here you can see that the default data type for I is the float value. It's a float. It means that there's it's a real number, right? 1.000, like something like that. It's not an integer. So if you want to make it integer, we can just say D type, data type is equal to what? Integer. I want to create a matrix with integers, so I can get the integer value like this. Right? So now let me create, and I say this M. Okay, just stick with the M. So we want to take the inverse of an M. But in order to take an inverse of a matrix, first it needs to be what? It needs to be a square matrix, right? So the number of columns and the number of rows should be equal. And I'm going to make this 5 by 5. Okay, so we have a square matrix 5 by 5. Now I'm going to take the inverse of it. The inverse of it can be or we can take the inverse of a matrix by using the NumPy library, and in NumPy library we have linear algebra module, and in the linear algebra module we have inverse function. Inverse function of M, you can see if the determinant is the greater than 0, then we can take the inverse. Okay, so if you look at it, we find the inverse of the value like this. I'm going to call this one M inverse. This is M inverse. Then what I want to do is I want to what we said what? A times A inverse should be equal to the identity matrix, right? That should be ones in the diagonal and zeros everywhere else. So I want to prove that by just multiplying M times, or I want to validate this equation by M times N inverse. Okay, so now here, let's look at here. If we just do the multiplication, it does not do the matrix multiplication, right? It does what it does do. It does the same thing here, like this. Okay, if you guys remember here, what does it do? It just multiplies element by element. So it's just gonna multiply this and the inverse of the first element, and this inverse of the first element in the second row, and so on. So if you want to matrix multiplication, what we need to do is the same here, MP dot. So MP dot, no, MP multiplication, sorry. MP multiplication, multiply. Or does it the same? Just a sec. Let me remember. And we can just confirm if it gives us an identity matrix, and this is correct, right? So let's look at here. No, it's not correct. Multiply is not correct. That MP dot, was it? Yeah, it was MP dot, sorry. Okay, my mistake. So if you look at here, the diagonal values are all, this here, it does not show us a good representation, but anyway, we can just get this is the fourth element, this is the fifth element. All the diagonal values are 1, so that's correct. But look at the other values. The other values, when you look at them, some of them 0 or exactly 0, but some of them are very, very, very small numbers, but not exactly 0. This is just because of the precisions of the numbers. Like, you know, computers cannot cannot calculate with infinite precision. There is a limited precision in the computer, so we can have these precision errors, right? But when you look at this, this is 10 to the minus 16, meaning that very, very, very small number. So we can just ignore it and say it is 0. Okay. So this identity matrix is fine. Let's now look at this one. Okay, so now I'm gonna give a small break. Then we're gonna come back with an example.
Hocam aradan önce bir şey sorabilir miyim ben?
Sure. Go ahead.
Dot product hocam sıra sıra aynı row ve şeyleri çarpmıyor muydu, kolumları? Yani normalde matris çarpımı yaparken daha farklı yapıyorduk diye hatırlıyorum da ben.
No, the dot product is to match multiplication. If you are in doubt, we can always check the documentation. Okay, let's check the documentation. So sometimes you cannot memorize all the functions always, but what you can do is just if you know what function. Okay, so you can go to Google. np dot. Okay, let's look at the numpy dot function. Dot product of two arrays is just this one. Let me see if there's a matrix one. If both A and B are 2Ds, it's a matrix multiplication. You can see that, right?
Okay.
If A and B are 2Ds, if A and B are 1D arrays, then it's an inner product, as we showed. But if A and B are 2D arrays, meaning matrices, then it's a matrix multiplication. But we can use also matmul. Okay, numpy matrix. Okay, we can also use this one, right? Same. Probably it's also calling the same function. So np.matmul does the same thing. Let me just, it's matrix multiplication. As you can see, it's doing the same thing. Okay. Any questions?
Will you upload the courses on YouTube?
All right, Kutay. I haven't, but I might be. I think I can download the. I'm recording this one, right? Let me
Yes,
check.
you are recording.
I'm recording right now, right? So let me make sure. Stop share. Yeah, I am recording. So I'm gonna download the video and put it on YouTube. Okay.
Nice, thank you.
Hocam
So,
Jupyter Notebook yükleyecek misiniz?
say again?
Jupyter Notebook'ları yükleyecek misiniz
Sure,
Nino?
sure. I'll also upload all the files we have done to Ninova.
Tamam, teşekkürler.
Okay, let's give 10 minutes breaks, then we will be back. All right, so okay, just a sec. Let me add your type. Okay. Okay, so now let's do a small example. You guys can hear me, right?
Yes.
Just
Yes.
let me see. I'm still recording also. Let me make sure. I'm still recording. Okay. So let's say we have let's say we have this set of equations. I'm trying to adjust. Okay, let's write it. If it doesn't work, we're going to change the numbers. Let's say I have something like this. Okay, 2 times x plus 3 times y is equal to 5, or let's say just 1x. Okay, and 2 times x plus 4 times y is equal to 10. I'm not sure if the numbers will work, but let's try and work this. So what I want you to do is first try to write this expression or linear equations as a matrix representation. Okay, so I want you to write the coefficients as a matrix, then x and y they are variables, and these are the right hand side of the equation. So try to write this one as a matrix presentation. I'm going to give you 2-3 minutes. Then we are going to do it again together. I'll give you a few minutes.
Can you repeat what should we do?
You are going to write this one as a matrix or matrix multiplication, something like this. Okay.
Okay.
I want you to something. Let me say x1, and this is x2, so I can do it better. x2, x2. So a times x is equal to b. Find the value of a, matrix A, vector x, and vector b. Bakalım isterseniz beraber. Şimdi ben o zaman şu şekilde yapalım. Şurada diyelim ki A maddesimiz, değil mi? Şurası A maddesi, şuradaki şeyler olacaktır. Ne derler? Değişkenlerin katsayıları olacaktır. 1, 3, 2, 4. X maddesini X vektöründe şu şekilde yazarsam ben X1, X2, X1, X2 ve eşitliğin sağ tarafını da direkt olarak bir vektör şeklinde şu şekilde 5, 10 yazarsam bunu elde ettim, değil mi? Şuraya bakarsanız ne yapıyoruz? Şu satırla şurayı çarpıyorum ve bak, şu satırla şurayı çarpıyorum. Neyi bulacağım? 5 yani hocam, değil mi? X1 artı 3x2 eşittir 5. Sonra şu satırla burayı çarptığım zaman da 2x1 artı 4x2 eşittir 10. Bu şekilde ne yapmış oldum? Şurası benim A maddesim. Burası X vektörüm. Burası da B vektörüm şeklinde oluşturmuş oluyor. Şimdi bunu bu şekilde oluşturduktan sonra benim size burada bulmanızı istediğim şey şu. X vektörünün değerlerini bulmanızı istiyorum. Bu denklemi sağlayacak X vektörünün değerlerini bulmanızı istiyorum. Bunu lineer cebir dersinden de hatırlıyorsunuzdur büyük ihtimal. Bu şekilde
elle buluyoruz,
lineer
değil mi?
bir denklemimiz varsa bunu nasıl bulabiliriz?
Hocam elle buluyoruz değil mi? Python'la değil.
Do you guys still have Python? If you guys have Python, you can just az önce Türkçe mi anlattım? Aklıma getirdim. So let me repeat this one, okay? So what we want is to represent this set of equations as a matrix equation, okay? So we have a matrix A and a vectors X and B. So if I just use the coefficients for matrix A, I will have matrix A something like this, right? 1, 3, 2, 4. And the vector of X, if I multiply this, the matrix A and vector of X, we can just, just multiply this row with this column, okay? 1 times x1 plus 3 times x2 is equal to 5. Then 2 times x1 and 4 times x2 is equal to 10. Then I can just write it easily as 8 times x is equal to 3. After I set up this equation, okay, after I set up this matrix equation, what I need to do is, I want to calculate the values that satisfies this set of equation. Values of x, x1 and x2 that satisfies this set of equations. So if I have a set of equation or matrix presentation like this, can you solve it for x? Right. So using Python, can you just do this and you can tell me the numbers or tell me this result from the chat. Let me give you 1-2 minutes, okay, also. Now we are going to do it together. All right, so we have 5 and 0. Anyone else found the result? Yeah. Back also found. Give me 1 more minute, then we are going to do it together. Sena also found. All right, so we set up the value matrix, something like this. It's an example, right? So we said is Ax is equal to B. So if I multiply the both sides with A inverse, right? So if I multiply this one, A inverse times A times X, and this is equal to A inverse times B, then what will happen? This will result in identity matrix, and identity matrix times X will be also X, right? So it will be just X is equal to A inverse times B, right? So I can easily find the X, value of X, by just multiplying the inverse of A with column vector B. So let's try to do this, and we had, let me write it, just a sec, what was it here? Okay, let's say A is equal to MP dot array. So we can manually create arrays using the NumPy array function, okay? Array function of a NumPy. And if you want to create a matrix, we need to write nested brackets, such as this. So every inside bracket will be the rows of the matrix. So this is what 1, 3, right? 1 and 3, and the other one is 2, 4, 2, 4. If you look at A, print A, let's say, you can see we just created the matrix. Next, let's create the vector B, right? Vector B is equal to, again, I'm going to create a manual array. And since B is just a vector or 1D array, we need to just use one square brackets, okay? Just like this. And B is equal to 5 and 10. All right, so then let me print B also. You can see B is like this. And X is equal to what we said, MP dot linear algebra dot inverse. This is going to take the value of inverse of matrix A. And I'm going to multiply this one with vector B, right? So for the multiplication, I can use MP dot. And I'm going to take the inverse of this one and multiply it with B. If you write print X, it will give me the values 5 and 0. All right. Okay, another important concept for vectors are the norms. Let me just write here.
Can I ask you a question?
Sure. Go ahead.
I was expecting to see 5 and 0, 5 and 10.
What we said?
10 is under the 5.
What was the result? 5 and 0?
Yes, 5 and under it 10. I was expecting like
no,
that.
It's C. So the multiplication of, since this is a 1D array, right? This is a 1D array and this is 2D array, and the result will be just 1D array, right? Just a vector.
Okay,
and in NumPy, vectors
24.
are just row vectors. Okay, this is just always row vectors. So
okay,
this doesn't have any shape. Or sorry, if you look at here, let me say, if you look at this one, x dot shape, you can see that x type shape. It means that it has two. It's a vector with 2 elements only. Okay, it doesn't have any other shape. If I did something like this, for example, if I did see here, B is what? B is an again just 1D array. Okay, if I prepare the B as a 2 by 1 matrix, such as like this, if I put brackets here also, is that correct? No, one bracket is missing, right? Yes, okay, so now B is 2 by 1 matrix. Now what you're going to say is correct. So here, this will be 2 by 2 matrix, and this is 2 by 1 matrix. If I multiply them, then it will be 2 by 1 matrix, right? Because now both of them are the matrices. In the previous one of them was matrix, one of them was vector. Okay, that's why the output the produced output was the vector. If I do like this, now you're going to get what you wanted. Is that understood?
Yes, thank you.
Mm-hmm.
Thanks.
So here, MP dot, or let me say, the MP dot function, if you feed one matrix and one vector, then you're going to get the output as a vector. Okay. Only if you feed or you give 2 matrices, then the output also will be matrix. So either you can do in this way or this way, it doesn't matter actually. But generally, since we are gonna want B as a vector, so then this will be better, I guess, right? Because we don't want it as a matrix, we want it as a vector. Generally, we want it as a vector, so I'm gonna change it to the original thing. So if I calculate this one easier because we don't have any second dimension here, so it will be easier to access each element. All right, so the norm is, we are using the norm generally to represent or to measure the size or the magnitude of the vector. Okay, so for example, if I norm the LP norm, let's say, we're going to say LP norm, and we are going to represent this LP norm, meaning that if we have p-dimensional vector, sorry, not p-dimensional, but a vector with p elements, okay, vector with p elements, then the norm of x in the p dimension or p space is equal to the summation of all elements or x to the p elements, but in the absolute values of x, okay? The absolute value of x to the p and the summation of all elements to the 1 over p. Okay, we are going to take the root p of this summation. Okay. In general, we are going to use L1 norm or L2 norm. Okay, especially in machine learning purposes, we are using mostly the L1 norm or L2 norm. Yeah, generally, we are using these two one. And L1 norm is equal to x. We're going to present this one as here. And what does it mean? It means that just the values or absolute values of the vector and summation of them. Okay, sum of the absolute values of the vector. Right. L2 norm. Let's say this one is this, and we are going to take the square root of the squares of the every element. X22 plus, or let me write it in more concise way. Xi square. So this is equal to the what? X1 square, X2 square, X3 square. Oops. 3 square X. K square. L1 norm also sometimes is called as Euclidean, sorry, not Euclidean, Manhattan distance or Manhattan norm. This one is called Euclidean. Okay. So if you look at in two-dimensional vectors, right? So let's say I have a vector of this. The Manhattan distance is just, this is here, okay? This is, let's say, A, B. LB is equal to A plus B. And L2 will be equal to the what? A square plus B square. So it will be this one, right? Okay. So this is it. Okay. I want to now, right. Let's do this, or let me give you an so what I want you to do is, let's say x is equal to mp dot random dot random. It's going to give you the random numbers between 0 and 1. Okay. And let me say 10. So x is like this. Find the LP, L1 and L2 norms of the vector of x, okay, in Python. Here, Pythons. Please find the L1 and L2 norms of these two vectors, of this x, vector of x. So L1 norm this one, L2 norm this one. The random here, this is MP random, this is the module, okay? The random module includes set of functions related with random numbers. So MP.random is just a module, or it's just a set of functions, it's not a function. So we are gonna use the random function, which is inside of MP.random. That's why we have two randoms here. Yeah, they are the same. Can use both of them. X.absolute or MP.absolute values are both the same. Okay. So, okay, so let's do it together. Right. So let's do this and give a small break also again. We'll be back later. Okay, so what we said is we want to take the L1 norm and L2 norm of these two vectors. L1 norm, let's say, is just equal to, what we said is take the absolute value of these values and then take the summation of it, right? Then MP sum, MP dot absolute value of X. And if you just print L1 norm, then we are going to get 5.37. Let's look at the L2 norm. MP dot sum, MP dot square root. First, we want to take the, if you look at here, we want to take the square root of all the summation of the squares, right? MP dot sum times X squared. And this will give me the L2 norm. Oops. Okay, this will be small also. 1.89. Also, we can do some, this is the explicit way to doing it, but we can use the function, I think if I remember correctly, should be norm, no. Let's see if there is, let me search for it. If you guys don't remember the function, I mean, it's okay to not memorize all the functions. You can never memorize all the functions. You just need to search for it. Okay, let's say numpy norm. Okay, it's in the linear algebra model. As you can see, it's in the linear algebra model. Okay, so mp dot linear algebra dot norm. Then we are giving the vector we want to take, and if you look at the documentation, the inputs are X, the vector we want to take the norm, and the order. Okay, so the default value is none. It means that, okay, let me see. Let's see, order. So you can use these norms, okay, these type of norms. So there you can see that there are lots of different norms. And what I'm gonna do is we are gonna use the L1 norm is this one, and L2 norm is this one, right? I think so. I guess so. If I remember. So let's check if it is correct. Was it or right there? Order is equal to 1. Again, so you can see we get the same number. If order is equal to 2, yeah, we get the same number. So L1, L2 norm, we can use this function as well. So let's give a 10-minute break. Also, I mean, I haven't covered actually all the linear algebra topics that we need, but as we come up to, or as we need the specific topics that you need to know, I'm going to explain before the explanation of the machine learning algorithms. But for now, let's say this is enough for linear algebra, and I'm going to mention a little bit about probability also, then we're going to finish this class for today. Okay, so let's give 10-minute break also, then we are going to continue. Let me just pause recording. Okay. All right. Probability. So the probability is just actually we are going to use probability just to measure the uncertainty of a system in a system. Okay, so there are some uncertainties when we're doing the machine learning problems. There will be some uncertainties. What are those uncertainties? Are the data. Right? When we collect data, we cannot collect exactly the observation. There will be always some error in data. So there will be some uncertainty, or there are some inherent uncertainties in data. If you know, for example, I want to measure the temperature of a room, but I can never, ever measure the exact temperature, right? This is the result of physical uncertainty, because I cannot make a perfect machine that can measure the exact temperature. Right? So also we are going to use, or we are going to introduce uncertainty in models also. Sometimes because the randomness brings us better results to us. Okay. For example, when we are doing, we are going to do later, let's say, k-means clustering. In k-means clustering, first we introduce random centers, okay? Because in order to start, or in order to implement the algorithm, we need to start somewhere, and we introduce this somewhere as random places. Also, for example, neural networks, or artificial neural networks, or deep learning. Right? So the weights of deep learning at the beginning needs to be random, or we need to give some random numbers. And these models are very, let's say, I mean, it can change the accuracy of this, the model. The given random parameters can change the accuracy of the model very, I would say, greatly, or let's say greatly. Okay. Okay, so let's start the probability, and you know this, the basic definitions. X is for example, if X is a random variable, P of X is the probability, or some say, or more in English term, likelihood of X is happening. Okay, you can define roughly like this. There are some other definitions, but we can define the roughly as this one. So as we said, this is probability, and I'm gonna go directly into let's dive into the things, the tools that we are gonna need. The marginal probability, for example. Marginal probability, but first I think we should define our for the marginal probability. I think we have to define for the marginal probability. It's better to define the joints, or let's go step by step. Okay, sorry, my bad. Let's go step by step. Let's define a marginal probability. It's not a good way to start probability. Let's start with the probability distributions. Okay? Distributions. Probability distribution, or let's say a probability distribution, is a description of the outcome of a random experiment. Okay, it's a description. For example, let's say I'm just tossing a coin. Let's say, right? We can head or we can tail, and there's the probability. If it's a fair coin, the probability of head comes is 0.5, and the probability of tail comes is 0.5. So the probability distribution of this experiment is just what probability that x is equal to head is equal to 0.5, or let me write it in more probability distribution. Probability of x is, if it is head, it is 0.5. If it is tail, it is 0.5. Right? This is the probability distribution of tossing a coin experiment. Right? And the probability distribution of, for example, rolling a dice, right? Then the probability of distribution for rolling a dice, probability of x is equal to what? If we can get numbers from 1 to 6, right? And if it is a fair dice, then all the probabilities will be equal. Then probability of getting 1 is 1, 1 over 6. Probability of getting 2 is again 1 over 6. Getting 3 is 1 over 6. 4 is 1 over 6. 5 is 1 over 6, and 6 is 1 over 6, right? So the major, the rule for, or the definition of the distribution says that probability of x, or each probability of x should be equal to 0. Okay, should be equal to 0, and the summation of all the probabilities should be equal to 1. Okay, this is the major definition of the probability distribution. All right, so if it is a discrete, the random variable x here, random variable x is a discrete value, right? It can be take 1, 2, 3, 4, 5, and 6, just only 6 values. And since it's just taking the 6 values, it's a discrete distribution. Then we call this one probability mass function, actually. It's for probability mass function. Okay. Or let me show it in a graphic. Let's say, all right, so 1, 2, 3, 4, 5, and 6. This is 1 over 6, right? This is the probability of x, and this is x. Then the values and the probability values are probability mass function will look like this. Okay. Our value, right? This is a discrete distribution. Discrete distribution. And it's called probability mass function. And we have otherwise what probability continuous distribution. And this is what we have now. We can take any real values, okay, between some, okay, the x can take any real values, not just some finite number, because in, for example, tossing a dice experiment, we have finite number of outcomes, okay? We have only 6 outcomes, so the number of outcomes we can count. But in a continuous distribution, number of outcomes we cannot count. You see, in the infinite numbers of outcomes, it has infinite number of outcomes. So then if the distribution has this type of property, then it's called the continuous distribution. So the most famous, or we are going to use the most one, is either uniform distribution or normal distribution. For example, you guys remember from probability class, right? Just the peak is 0. Okay, let me draw it a little bit better. Nope. Still good. Anyway, you get the gesture. So we can take any number, any point in this x-axis, right? And now, continuous discrete distribution, we are gonna, let's say, denote this value with the f function. In discrete one, we just say p, and here we are just gonna say f. And this is not probability anymore, it's actually density function. Density function. And in density function, again, and this one, probability density function, let's say probability density function. Again, all the fx values should be equal to greater than or 0, and now the sum becomes the integral, right? Integration of fx with respect to x should be equal to what? 1. This is the continuous distribution, and in the continuous distribution, you need to remember, we cannot get the probability of a single point, right? Let's say this is 0. Let's say it's a normal distribution. What if I ask you that, what's the probability that x is equal to 0? What do you guys think? What's the probability that x is equal to 0? If 0. X follows a normal distribution? Ria says 0. Is it the y value or
X value hocam.
Think about it. Okay, what we said, the output, or sorry, I'm sorry. The random variable, we can have infinite number of outcomes, right here. We have infinite number of outcomes. And I am asking you if one outcome is happening out of this infinite number of outcomes, right? So it is actually, this uniform distribution, it will be what? 1 over infinite. So it will be what then? 0, right? So probability of x is exactly 0, is just 0. So theoretically, actually nothing can happen, all right? So, so what do we do in continuous distribution? We only measure the probabilities of the intervals, something like this. Probability of x is less than 0, for example, right? What's this? Then this one is integral of -infinity to 0 fx dx. Okay. So this is 0. And this is what this is it. This is what is it. This is called the cumulative distribution. Right? So let's look at what the cumulative distribution is. Cumulative probability distribution, or for short, CDF. Cumulative probability distribution, CDF, means that is the probability of having value less than or equal to x. So fx we are going to represent this cumulative the probability density will not represented as small f x, and the cumulative density function we are going to say with capital F fx. Okay. So fx is equal to probability that the random variable x is less than some specified value of x. Okay. So for example, in our example, what I said, let's say I have a continuous distribution like this, and this is the value of x. F of x is just the area under this curve, okay, from -infinity to the x. So for continuous distributions, we are gonna, for continuous or for discrete, let's say first, for discrete, f of x, capital F, cumulative distribution is just, let's say, I, or let's say x. Since it's a countable number, we can use the summation function. X is equal to -infinity, say t. T -infinity to some value of x, p of t. Yeah. And for continuous, f of x is equal to, this time the integral from -infinity to the value of x, f of t dt. Right. Joint distribution if we have a univariate distribution or univariate variable, so if we have just one variable, we have one distribution, right? We have just one distribution. But if we look at the two variables, or I'm looking at the, for example, for weight and age of the class, okay? I want to look at the distribution of them together. Then I need to use joint probability. Joint probability distribution, now we have more than one variable. Okay? So in discrete, again, I mean, most are the same, but again, let's write it, okay? For example, probability of x is equal to some value of x, and probability of y, we have two variables, x and y, two random variables, okay? X and y. Probability of x is equal to x, and probability of y is equal to y. Okay? So here, this is the joint distribution. And for the joint distribution, let me see. Or if you look at the, if we have, for example, this is for the discrete type, and for the continuous type, what we have is, it will be like something like this: x is equal to less than x, and y is equal to less than y. Okay, we can write something like this one. And what I want to do here now, let's say I have a continuous distribution of x. And from this one, okay, let me see. Let me get an example of joint distribution. Just a sec. I want to get a graphic. You guys can hear me now?
Yes.
Where was I left? Where was I? Where did it go mute? I didn't realize.
I think the right
Huh?
picture.
Say again, Kutay?
You were creating the right picture last time I hear
Oh,
you.
this one. Okay.
Yes.
Okay. So no. Okay. Yeah. I'm gonna explain it together. Okay. So here now, look at here. So we have a value of x and value of y, right? Two variables, x and y here. Look at here. This x variable and this y variable. And both of them has their own distributions. You can see that. This is distribution of y, right? And this is distribution of x. If I join them, if I look at them together, their distributions together, I'm gonna get a distribution something like this. Here. Okay. I'm gonna get a distribution something like this. Then what I want is, sometimes I'm gonna want, okay, if I have joint distribution like this, I want a conditional distribution, meaning that I want to get a distribution, if you look at here, for example, when y is equal to, let's say, this is here, 0, right here, here. How does the distribution of x looks like when y is equal to 0? Okay, so I have, for example, I will have a distribution. When y is equal to 0, the x will look like this. The distribution of x will look like this. Okay? This is called the conditional distribution. Conditional distribution meaning that probability of x given that y. Okay? Probability of x given that y. So what I do is, what I want to do here is, what's the probability of x given that, in discrete sense, what is the probability of x is equal to x given that y is equal to y? Okay. So for example, let's do an example. Let's say probability of x, y is something like this. 8 times. Find a better example. Let's see. Good example. Let me just find the right numbers. Just give me a sec. Okay, so let's do this example. So we're gonna understand better. This one. Okay. All right, so we toss a fair coin 3 times, okay? We are tossing a fair coin 3 times and record the sequence of the heads and tails. So the only outcomes are the heads and tails. Let's say we assume that random variable x denotes the number of heads obtained, okay? So the x is the number of heads obtained. So what are the outcomes for x? There will be no heads, so 0. There will be 1, 2, and 3. So there are, how many outcomes are there? 4 outcomes, correct? And we also let random variable y denote the winnings earned in a single game, a single play of a game with the following rules based on the outcomes of the probability experiment. Okay, so player wins $1 if first edge occurs on the first toss. Yeah. If my first experiment or if my first toss is a head, I win $1. If my first head occurs in the second toss, I win $2. And if head occurs on the third toss, I win $3. And I will lose $1 if no head occurs. If there are no heads, I'm gonna lose $1. All right. So then we have two experiments, right? Two variables, x and y. Now I need to get the probability mass function, or joint probability mass function actually, of x and y, right? Of x and y. So we can have a matrix style, or we have a table style. So the number of outcomes for x, I'm just gonna put the table over here. Okay, insert, let's say I will have how many? 4 outcomes for x. How many outcomes for y, by the way? Y, what's the y? Denote winnings earned in a single play of a game with the following rules, right? So I can earn $1 if the first outcome is head. I can earn $2 if the second outcome is head. I can earn $3 if the third outcome is head. First, right? Then I can lose $1 if there's no heads, right? So if there's no heads, I can. So here also I have 4 outcomes. I can lose $1, meaning that -1 earning, let's say. And I can gain $1, $2, and $3. So there are also just 4 outcomes. All right. So I'm gonna write 5 by 5 table should be enough for me, I think. Let me see. Okay. Let's just use a simple table. So let's say this is x and this is y. And for x, I can get 1, 2, 3, or sorry, 0, right? 0 heads, 1 heads, 2 heads, or 3 heads. For the outcomes, I can earn, or I can lose $1. I can earn $1, I can earn $2, and I can earn $3. Okay, so let's look at it. So what's the, if y is equal to -1, or let's say, only and only if there are no heads occurs, I can lose $1, right? Only and only if there are no heads occur, I can lose $1. Then what's the probability that this one, right? What's the probability that this one is what? 1/8. Is that correct? Because what's the probability that there are no heads? It's just probability that, so all of them will be tail. It's just 1/2 times 1/2 times 1/2, and it will be 1/8. Okay. And if x, or number of heads, is 1, I cannot. So probability that I will earn I will lose $1 is 0. If there are 2 heads, I will lose $1 is 0. If there are 3 heads, I will lose $1 is -1. Again, 0, right? So what's the probability that I'm gonna earn $1 if x is equal to 0, meaning there are no heads? If there are no heads, I cannot gain, or I cannot win $1, right? If there, what's it? If there's 1 head, it can be either in the in the first toss, it can be either in the second toss, or it can be either in the third toss, right? Right. So I can earn $1 if it is only in the first toss. It means that the probability of this one is 1/8, right? Because the probability that there will be 1 or let's say this means that the first head, this is the number of heads, right? And this is the first head is, this means that the first head comes in the first toss. So this can only happen where head, tail, and tail. So the probability of this one is 1/8. Okay. If there are two heads and the probability that the first head is in the first toss, right? It can only happen how? Like this: head, tail, tail. Sorry, head, head, tail, head, tail, head, right? Here in this one. So this will be what? 2/8. In two conditions, these two satisfied only by two outcomes. Again, if there are three heads, so here, head, 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 the probability that I'm going to win $1. Okay, so this will be again 1/8. Yeah, this condition can only happen here like this, right? 1/8. So here again, if there are no heads, I cannot win. If there are one heads, the probability that it's gonna happen in the second toss is only satisfied this one, right? Tail, head, tail. If there's just one head, then the probability that 1/8. Again, this one, if there are two heads, the probability that it's gonna happen in the second head, it will be just, what will it be? The first head, it can be just this one, right? Head, head, because the first head occurs in the second toss. So this will be also 1/8. And if there are three heads, meaning that this is head, head, head. So the first row can never in the first head can never be in the second toss. Then the probability of this one will be 0. And here again, I cannot. If there are 0 heads, I cannot win anything. If there are one head, I can win, and the only possible combination is this one: tail, tail, head, right? In the third, the first head is in the third toss, so this is 1/8. And here it means what? If there are two heads, there can never be any experiment that the second toss is a head, the first head. So there will be, this will be 0. Again, this will be 0. So my probability mass function will look like this. Let's see, all of them are greater than 0. And if I sum of them, this is 1, 2, 4, 5, 6, 7, and 8. So the sum is also 1. So that looks like correct. So there is a question. So this one we're asking, right, Pınar? So okay, let's look at here. What does X means? X means that number of heads I obtained, right? And here it means that $2. I'm gonna win $2. How can I win $2? Only and only if first head occurs in the second toss, right? First head occurs in the second toss. Then, so let's look at all the outcomes that has two heads, right? So what can I can have head, head, tail, head, tail, head, and tail, head, head, right? Now what I'm looking at here is where is in this all the outcomes, which outcome the first head occurs in the second one. So the first head here, the first head occurs in the first one, so this is out. Here the first head also occurs in the first one, so this is not correct. Here the first head occurs in the second one, so the only outcome is this one. Okay. So that's why we have 1 over 8 here. Okay, so now this is my probability mass function. According to this one, my question to you is this here, joint probability. So I'm asking you, what's the probability that x is equal to 1, given that y is equal to 2? Let's say. Okay, so what I'm gonna do, look at here. Okay, so y is equal to 2 here. Okay, right? Oops. Y is equal to here. What's the probability that while y is equal to 2, x is equal to 1? So it's just what? 1 over 8, right? Wow. So if I'm gonna ask you this one, what's the probability that x is equal to 1, regardless of y? Okay? This is conditional distribution. Right? It's a conditional distribution, and this now here I am excluding y, or I am, okay, I say summing up y. Then what happened? Let's look at here. So x is equal to 1. Okay. So x will be equal to 1, and y can be anything you want. Right. And this is called the marginal distribution. So what I want is I want a probability of x. So I need to sum up, or I need to get rid of y. In order to get rid of y, I'm going to sum up all the y values when x is equal to 1. Okay? So what I'm going to do is I'm going to get all the y values for all y, probability that x is equal to 1, given that y is equal to y. Yeah. And this is equal to, if you look at here, when x is equal to 1, when x is equal to 1, y can be minus 1, 1, 2, and 3. And the probabilities, I'm going to sum up all these probabilities. So it is 0 plus 1 over 8 plus 1 over 8 plus 1 over 8. And this is 3 over 8. So in this distribution, the probability that probability that x is equal to 1 is 3 over 8. Right? Even without looking at here, we can also calculate, because what x denotes the number of heads obtained, right? So in how many combinations I can get 1 heads in just 3 combinations, right? So head, tail, tail, head, tail, and tail, tail, head. So out of 8 combinations, 3 of them will include only 1 head. So thus, the probability will be 3 over 8. The marginal distribution also. So this is for the discrete part. If I have a continuous value, right? If I have a continuous distribution, then the marginal distribution will be is equal to, for example, from here, if I want to calculate the f of x, what I need to do is sum up all y's from minus infinity to infinity, f, x, and y dy. So I'm going to sum up, integrate y from minus infinity to the infinity. Okay, so this is the marginal distribution. And lastly, I want to talk about the bias formula, bias rule. That's actually the Bayes machine learning, or Bayes statistics, is a branch of an statistic. Okay, it's a huge area. So the whole area, or whole statistics comes from this simple formula. Okay, So before that, let's say probability of X given that Y is equal to probability of Y given that X times probability of X over probability of Y. Okay, this is the Bayes rule. So probably I think we are out of time. I'm going to do one example about the Bayes rule next week, but today I'm going to finish the class because this is an important rule. Okay, or maybe I can give you an homework. I'm going to try to prepare a homework for you guys. And for this one, this is important. This part is important because there are lots of algorithms there that are depends on the Bayes rule. Okay. So for today, let's finish up this class. If you have any questions, I can answer. Do you have any questions?
Hocam bir şey sorabilir miyim ben? Sesim geliyor mu hocam? Gelmiyor herhalde.
Kerem, I cannot hear you. Can you speak a little bit louder?
Geliyor mu hocam sesim?
Şu an geliyor, evet.
Okey. Hocam önerebileceğiniz bir kitap var mı? Genel olarak machine learning hakkında. Yani ders
For
bağlantısı
machine learning part or for the
Machine
algebra
learning
part? Or, huh?
Machine learning için hocam.
For the machine learning part, I mean, there are lots of good stuff, I think. Let's see, just a sec. If you want to really learn the mathematics behind the machine learning, or the thing is this book is a fundamental book, Bishop's pattern recognition book, pattern recognition and machine learning. Let me find the link for it. Okay, this one. This gives you the fundamental of every algorithm, almost every algorithm. It's a big book. And again, the mathematics book, the elements of statistical learning, this one is also a good book. You can check these two out. Okay.
Teşekkür ederim hocam.
Hocam ben de bir şey soracaktım. Bu probability ve algebra fundamentallarının ne önemi olacak bizim machine learning'de acaba?
Say it again, Emre.
Hocam bu probability ve bu algebra gördüğümüz algebraların ne önemi olacak, bu matrisleri ne önemi olacak? Machine learning kısmına geçtiğimiz zaman.
All the calculations that we are going to do in machine learning algorithms will be based on this stuff. You're going to see. I mean, we are going to start from linear regression next week, and you're going to see that it's all based on this stuff. Okay.
Anladım. Teşekkürler.
Actually, for the linear algebra, if you took last semester, last year, my END 201, I showed you guys, we can use this formula. Okay, we can use this formula to represent linear regression. Okay, this formula to represent linear regression, and we can solve, or we can calculate the parameters of linear regression by using just what we have done here, like this. Okay. So next week I'm going to show you how to do that. Any question? No? Okay. So I'm going to see you guys next week. We're going to start with linear regression, then logistic regression, the basic stuff, then we're going to come to the more advanced algorithms in machine learning. All right. See you guys later.
Yeah.
Have a nice
Hoşça
week.
kalın hocam.
Nice weekend.
Görüşürüz.
Okay, so just leave.